Good? Okay. Hello. My name is Jon Olav Grepstad, co-founder and business development manager at Tunable, which is a company I'll be representing today. And I'll start with a little story explaining why we have a cute little boy smelling flowers on the first slide here. So, robots have long since surpassed humans in mechanical speed and precision. Cameras can see in the dark and details that our eyes can't even resolve, and microphones can sense pressure changes that our ears won't even notice. But when it comes to smell, our nose remains remarkably competitive. For some gases, even sophisticated laboratory equipment can't keep up with the nose when it comes to its combination of selectivity and sensitivity. And that's the vision of Tunable. Now, in essence, the nose is just a gas analyzer. So in less poetic terms, you could say that we are making a multi-gas analyzer that's competing or wants to compete with the human nose. So that brings me to the title of my talk, One Hardware, 500 Gases, a tunable MEMS filter enabling next generation multi-gas infrared spectroscopy. And the cute little boy has been exchanged with the key component in our scheme, a MEMS filter that you see here compared to a €1 And that's the basis of my talk today. Now, on the agenda, I'll start with explaining or telling you who Tunable is and what we make and where our products are deployed today. I'll try to position ourselves in the market and compare us to alternative approaches before I continue explaining how our MEMS chip works and how it's made. And finally, I'll summarize explaining what our uniqueness is and how that, or what it means for future and current applications. So first, Tunable. We are a company located in Oslo, Norway. We have been selling, or we were established back in 2015 and selling products since 2019. We are 30 employees that are spread across sales, development, and production. And we do everything in-house in this building that you see in the picture here. The three products that we have developed this far, you see here. You have the T1000 series, which is a fuel gas analyzer, EX certified. You have the 2000 series, which is a trace gas analyzer, measuring in the ppm levels. Both the two analyzers to the left are initially designed for the marine sector. And then you have the closest thing to a digital nose that we have this far. It's a smaller analyzer, also measuring in the ppm level range. Basically a general purpose analyzer that can detect any gas that absorbs between 7 and 14 or 15 microns. So we have focused on the marine segment this far, where our two T1000 series and 2000 series are applied. What we do there is, for fuel gas, we measure the quality of boil-off gas. And boil-off gas, that is gas that evaporates from LNG carriers, and that gas is used as fuel in these vessels. Now, for the ship owner, he wants to measure the combustible compounds in that fuel stream. And that's to avoid paying for nitrogen, which is also in there. So that's what we're using the T1000 for. Now, the 2000 series is basically used on the other end. It measures emissions. And that's done because that's mandatory in many countries. And especially in many European countries, you also have to pay for what you emit. And it turns out that if you measure what you actually emit, that can be very cost efficient compared to paying those taxes based on tabulated values. Circling back to the T1000, I can actually mention that this has been particularly attractive. Previously, boil-off gas was measured by gas chromatography, but we see more and more LNG carriers now turning to our product. We have actually 20% of the current LNG fleet using our analyzers, and 80% of new builds. So replacing GCs in that case, which we're very proud of saying. The 2000 series also used for another application. This is for monitoring in dynamic controlled atmospheric rooms for fruit. So the thing there is that you want to get the oxygen level as low as possible. In order to do that, you need to measure when fermentation is initiated, and that you can do by measuring ethanol and ethylene. So in this case, we measure ethanol and ethylene in these rooms to enable the oxygen level to go as low as possible, making the apples last longer, basically. T3000 also used in the fruit industry, here to optimize the atmosphere in ripening rooms to ensure that the ripening process continues as planned. So these are just a few examples, actually, of where we are deployed. So just to give an example that our technology works, it works in demanding environments like the Marines, and it provides value to our customers. So where do we place ourselves in the market? And there you go, yeah. To explain that, I find it useful to divide the gas sensing space into two groups. So one group of analyzers, they're cost-effective and they're easy to deploy in the field. Here you find NDIR, electrochemical, metal oxide semiconductor, metal oxide, and Pellicer-based analyzers. They have a decent accuracy from ppm and up, very good, typically pretty cheap, can measure 1 to 3, 4 gases, and easy to use. Now, in the other group, you have more expensive stuff, and that's also more used in the laboratory often. Here you find FTIR, photoacoustic sensing, gas spectrometry, mass spectrometry, and TDLAS, laser-based systems. And these are very accurate. You can go down to PPT in some cases, right? And also you can measure many gases often. But they are typically very expensive and not as easy to use. So what we try to do is to place ourselves in the middle there. By making something that is easy to use, we can measure many gases at the same time with relatively cheap. And while we can't boast about PPT accuracies, we can go down to ppm and a little bit below for some gases. The way we do that is by infrared spectroscopy, as I said initially. So for those of you not familiar with this technique, it's illustrated here. You have an infrared source to the left. You can think of that as a light bulb producing all wavelengths of light. Next, you have an optical filter, which filters out the narrow band of frequencies from this broadband source. That light goes into a gas cell, and if the cell that you're looking for, the gas that you're looking for, absorbs this red light, you can see a reduced amplitude on the detector. And that amplitude reduction is translated into a gas concentration. Now, if you want to detect 2 gases, you need a second wavelength typically. 3 gases, you need 3 wavelengths, and so on, and that's how you make a multi-gas analyzer. So we can detect up to 8 different gases before things become overly complex. And the complexity here is basically that in order to translate these detector values on the left side here, you need some kind of, you need to solve a complex set of nonlinear equations, basically. And the way we do that is that we use a neural network that we train. So each analyzer that we send to our customers are trained in-house on a fixed known set of gases, enabling you to recognize unknown mixes when you're out in the field. Now, for those specialists out there, you might say that this is very, very similar to many other traditional gas sensing schemes. And I agree. For example, if you have a fixed set of filters mounted to a rotating filter wheel, you would basically explain the scheme in the exact same way. Now, the difference between that and us is that we don't have a fixed set of filters which are rotating. For example, we have one filter and we tune the transmission through that filter electrically. But that gives us some advantages. Well, first of all, we don't have any moving parts, so we're very robust. We can tune the transmission continuously, which means that we can detect both very low and high concentrations. And we can also introduce some new features that we collectively have called gas fingerprint recognition. So one of these things is diagnostic sweeps that you can use to detect unknown species or contaminants. And you can also do complex or classification of complex mixtures. For example, enabling rot detection in fruit. So I've included a couple of user cases here to explain that. So what you see here is a case of a customer which ordered an analyzer that was supposed to measure ethanol and ethylene. And out in the field, it turned out that something was very strange. It didn't really work as intended. So we tried to figure out what it was. And the first thing we could do was to scan through the entire spectrum to look for any contaminants or new gases that could have come into the picture that we weren't aware of. And it turned out that, yes, there was one, a new one, a third gas. And after looking at the possibilities, it turned out to be ethyl acetate. So what we could do in that case was to use simulated data to make a new gas model, including a third filter position, and everything was done in the field without returning the instrument to us. So in some cases, at least, it can be a very powerful tool to fix things without sending the units back for further calibration, for example. Second example here is from rot detection, where you can show how, where I've shown how you can use the spectrometric function of the analyzer, the scanning capability, to classify whether fruit is rotten or if it's good. And the difference between different fruit is also apparent. Now, this is used, for example, to qualify a batch of bananas without having to dig through the whole batch looking for that one rotten banana. You can instead just smell that there's something wrong with this batch, so we'll have to check that. Or if it's not, you send it out to the consumer. Okay, so all that is possible using this chip, right? Initially shown on my second slide. So I'll now explain how that works. Basically the core of our solution. And it's based on something maybe pretty familiar to many of you. It's called a Fabry-Perot optical filter. That was developed way back in 1898, or first demonstrated back then. Back then, the Fabry-Perot instrument looked like the one to the left. And that was done by two French scientists, Charles Fabry and Alfred Perot. And now, a couple of years later, this is what it looks like. That's our Fabry-Perot mounted on its control circuit board. So Fabry-Perot, to explain how that works, I think it's nice to see how it works in the simplest case. And in its simplest form, a Fabry-Perot is just two parallel, partially transmitting mirrors that are these yellow lines that I've drawn here. And to see how that works, we'll just try to send a beam of light in from the left and calculate what the transmission is. So naturally, the first thing that happens is that you'll get a strong reflection from the mirror. And then you get additional reflections from the multiple round trips that the field takes between the mirrors. And you also get a set of transmitted fields. Now, naturally, two mirrors should reflect a lot of light. So for most wavelengths, you get very low transmission. But for certain wavelengths, where this condition is fulfilled, you can get very high transmission, all the way up to 100%. And that creates these nice peaks in the transmission spectrum that you see to the right. These peaks can be moved back and forth by adjusting the distance between the mirrors, and you can adjust the bandwidth of each peak by adjusting the reflectivity of the mirrors. Now you can also notice that a Fiber Pro does not produce a single band optical filter. You get these so-called higher orders of transmittance to the left of the first order. So in order to make a single tunable optical filter, we have to introduce a stop band, and we limit the tuning range. But there you go, a tunable optical filter. Now, of course, this is in theory. In real life, there are some obstacles. For example, lossy materials and such. So we're going to try to mimic this result using real parameters. And I'm going to tell you that it won't be perfectly matching. But we'll try. So the way we do it is that we start off with a pair of silicon wafers. And I've tried to make this comparable to the theory example. So to the left, you have the system. To the, to the right, you have the system. Left, you have the system. Right, you have the resulting transmission. So 2 silicon wafers, starting with that, sending the light in from the left, obviously does not give you the theoretical transmission, right? It looks very different. So we'll start by adding some high reflective surfaces on the inner sides of these silicon slabs. And at that point, you can start to see some features that are kind of similar to what we saw in theory. But you still have this high frequency component on top of these slower, or these resonance peaks. And that's because of the parasitic resonances that remain in the silicon slabs in themselves. So to solve that, we have to introduce some anti-reflective surfaces in order for basically to only have the gold surfaces remaining in our optical system. So we do that. We introduce some anti-reflective coatings on the outer surfaces. And in this case, the light will come in from the left, won't see the first surface, and the first surface that it sees is the gold. Then the second surface is a second gold surface, and then exiting, there will be a new anti-reflective coating, so it won't see that either. So basically, what you're left with are 2 gold surfaces, 2 reflective surfaces, right? And in the plot, you see that, yes, at least for around 2 here, you do have a nice little peak, which is pretty clean. For the lower wavelengths, it doesn't really look as good, and that's because the anti-reflective coating is not really efficient over the entire region. It has a limited bandwidth. Now, if we compare that to the theoretical plots, we see that there are a couple of other differences too. For example, the transmission is quite bad. In this case, only 20% of the theory, and that's because we've used metal as our mirrors, and metal is a lossy material. And you can also notice that the position of the peak is slightly shifted, and that's because the effective reflective surface is not located exactly at the gold-air interface. But nonetheless, we've made a tunable, or not a tunable yet, but a filter, which is defined by a pretty narrow peak. And now we have to try to move that peak back and forth. And to do that, we have to move our silicon slabs. And to explain that, I'll continue to the real device, which looks like this. And what you're looking at is 2 silicon chips that have been bonded together, and the top chip composed of a piston that hangs in a membrane, and on top of that membrane, there's a material that allows you to bend that membrane up and down. So-called PCT, lead zirconium titanate, which is a piezoelectric material. That top chip is made like you see here. It's made on wafer level using semiconductor fabrication techniques, or MEMS techniques. So starting with a silicon on insulator wafer, we deposit PCT, pattern that, we do front-side etch, and we do back-side etch to release the piston. And in a simpler processing run, we make a bottom chip. We bond the 2 together. That can be done either on wafer level or on chip level. And the same thing goes for anti-reflective and mirror coatings. So what you're left with then is a chip that looks like this. has 6 actuator segments that can deform this membrane, allowing you to adjust both the gap between the mirrors, and you can operate this and tip and tilt adjustment to ensure the mirrors are parallel, and you can operate it statically, locked to a specific gap or wavelength, if you will, or dynamically scanning continuously. Now, continuing to what this looks like in real life, you have measurements here using FTIR, showing that we can scan our filters from 2 to 6 and 6 to 15 for 14.5. So we work in the range from 1 to 15 microns. We can't cover the entire range with one filter, but by tuning the materials in our coatings and our thicknesses in our coatings, we can basically tailor our filters to our customers' needs. And to do that, we naturally need the deep thin film expertise. So we have invested in advanced coating equipment, and have experts in the field working for us. So we can tune the coatings in order for it to match the customer needs. Basically, so for example, for a high tuning range, you can use metal coatings. In that case, you would typically have the low transmission like you saw in the material example that I showed. Or if you need high transmission, you would go to the electric coatings and then maybe compromise on the tuning range. But we can at least play around here with some degrees of freedom. So in summary, what that boils down to when it comes to the filter, you see here, we have an optical aperture of 3 millimeters. We work in the range from 1 to 15 microns. Our full width half maximum is pretty wide. It's from 1 to 4% of the center wavelength. We can operate dynamically with a frequency of up to 250 hertz and statically. And our center wavelength precision is below 1 nanometer. Temperature range from -20 to 60 and expectancy, lifetime expectancy of above 10 years. Okay, so in summary, if we incorporate that filter into a testing scheme, currently being infrared spectroscopy, what that means is that we can detect, as far as we have identified, 500 different gases. Now, we can't detect all 500 gases at the same time. We can do about 8 at the same time. But we can do that with a detection range from 1 ppm to about 100%. We do use zero gas as a calibration, but we don't have any calibration gases. We don't require any calibration gases in the field, except for nitrogen. Robust system said as a result of no moving parts. And since we have a scalable wafer level production of our core component, that in the end enables miniaturization, of course. But for high volumes, we expect to be able to compete at a good price. So for current products, what this boils down to is that we can design systems and make products that detect specific gases that compete with gas chromatography. And we have the scanning capability that means that we're entering the space only covered by FTIR before. For future devices, what we hope to do is to basically do a general calibration in our production facility, enabling the user to configure the analyzer to detect whatever gas he needs or in the field, as long as they absorb in the infrared. So with that, I thank you for listening. And if you have more questions, you'll find us at booth 1356.